There's a Category 5 scale for a kind of storm most people have never heard of, and the storms it measures are aimed at the United States every single winter. They are called atmospheric rivers, and the name is almost literal. Corridors of water vapor, flowing through the sky, hauling moisture up out of the tropics. A strong one carries the equivalent of 7.5 to 15 times the average flow of water at the mouth of the Mississippi River through the air, over the coast, in a matter of hours. Scientists at Scripps built a scale for them running from Category 1 to Category 5, exactly like hurricanes. And a Category 5 arrives roughly every 3 to 5 years. That is not the disaster. A Category 5 on its own is survivable, and California has taken plenty. The disaster is what happens when they stop arriving one at a time, line up over the same coastline, and do not stop for 45 days. What the United States Geological Survey found when it modeled exactly that, and the reason the last time it happened, the state of California went bankrupt, is where this goes. But first, what these things actually are. Look at a satellite image of the Pacific during a winter storm, and it does not look like a hurricane. There is no eye, no spiral. Instead, there's a long, bright, narrow band of moisture stretching thousands of miles across open ocean, from somewhere near Hawaii up toward the west coast, and it hits the coastline like a fire hose held in one position. That is an atmospheric river. It is a concentrated corridor of water vapor in the lower atmosphere, moving moisture from the tropics toward the mid-latitudes. NOAA describes them plainly as rivers in the sky, and the comparison holds up better than most weather metaphors. They are narrow, they flow, they have a direction, and they carry a measurable volume of water. That volume is the part that stops people. According to NOAA's Physical Sciences Laboratory, a strong atmospheric river transports water vapor roughly equivalent to 7.5 to 15 times the average flow of liquid water at the mouth of the Mississippi River. An average atmospheric river already carries about the same as the Mississippi's entire average flow. The strong ones carry that many times over, invisibly, above people's heads. And here's the thing that makes them different from every other extreme weather system. The West Coast cannot live without them. A small number of these storms each winter deliver a very large share of California's total annual precipitation. They fill the reservoirs, they build the snowpack in the Sierra Nevada that feeds the state through summer. In a dry year, the arrival of an atmospheric river is genuinely good news, and forecasters say so, which is exactly why the scale that was built for them is unlike any other scale in weather. In 2019, a formal intensity ranking for atmospheric rivers was published. It was developed by Marty, director of the Center for Western Weather and Water Extremes at the Scripps Institution of Oceanography, working with Jonathan Rutz of the National Weather Service and other collaborators. It runs from Category 1 to Category 5, and the categories are named weak, moderate, strong, extreme, and exceptional. But the way it measures is where the real insight sits. It does not rank these storms only on how much water vapor they are carrying. It ranks them on how much water vapor they carry combined with how long that transport lasts over a given place, measured across a 24 to 48-hour window. Ralph's team found that duration was what actually caused the greatest impacts. A fire hose pointed at a hillside for 6 hours is weather. The same fire hose held on the same hillside for 2 days is a disaster. There is one more thing about that scale that makes it genuinely unusual. The Saffir-Simpson scale for hurricanes and the Fujita scale for tornadoes measure one thing: damage. There is no beneficial Category 3 hurricane. The atmospheric river scale deliberately covers both ends. The low categories are classified as primarily beneficial, the high categories as primarily hazardous. It is the only major weather scale that has to describe a storm as good news at one end and catastrophe at the other, because it is measuring the same phenomenon doing both. In practice, the categories describe completely different days on the ground. A Category 1 is a wet, gray stretch that tops up a reservoir and barely makes the local news. A Category 2 or 3 is a serious winter storm. Flooded intersections, road closures, a swollen river, the kind of week the West Coast handles every year. Category 4 is where the balance tips. Still delivering water the state needs, but doing enough damage that the cost starts to outweigh the benefit. Category 5 is the exceptional one, classified as primarily hazardous, where the water arriving has stopped being a resource and is only a problem. Many of the ones that reach California come along a route so consistent it has a nickname: the Pineapple Express, an atmospheric river that draws its moisture from the warm ocean near Hawaii and runs it northeast into the west coast. Warm source water means enormous moisture content, and it also means the storm arrives comparatively warm, which matters far more than it sounds, because a warm storm dumps rain on the mountains, where a colder one would have left snow. So where does the catastrophe sit on that scale? According to Marty, Category 5 atmospheric rivers, the exceptional ones, classed as primarily hazardous, come along roughly every 3 to 5 years. Every 3 to 5 years. That is not a rare event. California has absorbed them repeatedly, and the state is still standing, because one exceptional storm arrives, does its damage, and then the sky clears and the ground drains. Everything about that changes if they arrive in a line. That is the scenario the United States Geological Survey decided to model, and it is called ARC storm, short for Atmospheric River 1000. It was built in 2010 by a team led by Lucy Jones of the USGS Multi-Hazards Demonstration Project. Rather than inventing a storm, they took two real ones that had genuinely hit California, a Southern California storm from January 1969 and a Northern California storm from February 1986, and ran them back to back. What they modeled was 45 days of it. Not one storm, not a bad week. A conveyor belt of atmospheric rivers striking the same coastline in sequence for a month and a half. Here is why that specific structure is so much worse than any single storm. And it is not really about rainfall totals at all. It is about the ground's ability to absorb. The first storm in a sequence lands on ground that can take it. Soil absorbs water, rivers rise and fall, reservoirs have room, and the mountain snowpack holds some of it back. That is a normal wet week. The second storm arrives on saturated soil, so far more of it runs off immediately instead of soaking in. The third arrives on saturated soil and rivers that never came back down. By the fourth and fifth, the reservoirs have no room left to absorb anything because they have already been filled and the operators are forced to release water downstream into rivers that are already high. At that point, the system is not managing water anymore. It is passing it along, and every additional storm goes straight through to whatever is at the bottom. In California, what is at the bottom is the Central Valley, and it has one door. Nearly everything drains through the Sacramento-San Joaquin Delta, a single maze of channels where the Sacramento and San Joaquin river systems meet before reaching San Francisco Bay. Upstream of that door sits an enormous network of levees, much of it old, holding water back from farmland and towns that in places sit lower than the river beside them. When the inflow exceeds what the door can pass, the water does not stop arriving. It backs up and it spreads. The USGS modeled the result. The Central Valley becomes an inland sea roughly 300 miles long and more than 20 miles wide. About 25% of every building in California takes on water. More than 1.5 million people have to be evacuated. The damage lands between $725 billion and $1 trillion, more than the major earthquake scenario the state has spent a century preparing for. And this is where it stops being a modeling exercise, because that sequence has already run once with people watching. In the winter of 1861 into 1862, it rained across central California for 43 consecutive days. More than 10 feet of rain fell. The Central Valley turned into an inland sea of almost exactly the dimensions the modern model produces. On the 10th of January 1862, the day Leland Stanford was inaugurated as governor, the levees around Sacramento gave way, and the capital went under 10 feet of water. The damage came to around $100 million in the money of the time, roughly $3 billion today, and the state was broken by it. The governor, the legislature, and state employees went unpaid for a year and a half. 43 days then, 45 days in the model. The scenario is not imagination. It is arithmetic run on something that already happened. One line has to be said plainly and then left alone. Arc storm is a planning scenario, not a forecast, and nothing is being predicted for any particular winter. What has changed since 1862 is not the weather. It is the mountains. In 2022, Daniel Swain of UCLA and his co-author Xingying Huang, working with UCLA and the National Center for Atmospheric Research, rebuilt the megastorm with climate change included and published it in Science Advances. Their headline finding was that an event capable of catastrophic flooding is now roughly twice as likely as it was. The mechanism is snow. When an atmospheric river hits the Sierra Nevada in cold conditions, much of that water arrives as snow and stays on the mountain for months, releasing slowly, which is precisely what California's reservoirs were designed around. Warm the atmosphere, and the identical storm delivers the identical water as rain, and rain does not wait. It runs off during the storm, immediately, down into a valley that is already full. The study projects end-of-century storms generating 200 to 400% more runoff in the Sierra Nevada. The mountain range that used to be California's largest reservoir is turning into its largest funnel. There is one more reason this hazard is harder to prepare for than an earthquake or a hurricane, and it comes back to that duration insight. A hurricane has a center that can be tracked and a landfall point that can be forecast days ahead. An atmospheric river has no center. It is a band, and what matters is not only where it hits, but how long it sits there and whether another one is queued behind it. Forecasting a single storm's arrival is now fairly reliable. Forecasting whether the atmospheric pattern will lock into place and send 5 of them down the same corridor is a far harder problem, and it is the exact question that decides whether a winter is wet or catastrophic. By the time a sequence is unmistakable, several of the storms have already landed. So the picture is this: a category scale that runs to 5. Exceptional storms arriving every 3 to 5 years is a matter of routine. A state whose entire water system depends on those storms showing up, and a documented case in the written record of what happens when the sky simply does not turn off for 6 weeks. Subscribe for the real numbers on the next one, verified and in full.